So we are going to be discussing the adjoint method, which is going to be solving this for large problems. So let's first motivate this by giving you a very small example. So I want to minimize a j of s subject to a particular equation. So don't use a differential equation yet. Let's say I already have a discretized differential equation, and it's even simpler. So let's say j is not a function of s. J is just a function of u. Usually it's a function of u and s, right? Usually it's a function of u and s, and such that the differential equation we are satisfied is just the u is equal to a times b of s. So b of s is a vector function of s, and u, the solution, is just equal to a matrix times this vector. So I want to ask you, this. If the objective function is linear with respect to u, that is, j is equal to a vector c transpose u plus d, let's say. All right, so it's a linear scalar function of u. Can I solve this problem without ever computing the solution u? So the challenge is, how do I solve this optimization without computing u? Anybody? Yes? Yes. So the answer I heard is, can I just substitute this equation into the objective function? We can do that. So let's see. If we substitute the equation into the objective function, j is going to be c transpose times a times b s plus d, right? So computing the solution involves multiplying a with b, but here I can actually multiply c transpose with a first. So the procedure is, if I compute, let's say I call it u hat is equal to a transpose times c, then j is going to be equal to u hat transpose times bs plus d. Right? So if I rewrote the objective function directly as a function of b as opposed to as a function of u. So now, as long as I have this u hat, I can evaluate this objective function again and again by just changing b without ever doing this matrix vector product again. Right? So yeah, this seems to be a simple trick for a very special case. But this can be really generalized, because what we are actually doing here is just multiplying the matrix vector sequence in a slightly different way. The traditional way, when we are dealing with a big equation, is that we solve for the solution and then substitute the solution into the objective function, evaluate it, and then if we are not satisfied with the answer, we choose another design parameter, right? It's just like we are using experiments to do the design, like when the Wright brothers were designing their airplane. They build an airplane, they fly it. Does it work? If it doesn't work, they change the airplane, fly it again. So this is the traditional way of using simulation, using computation to design optimize things, is to solve for the solution again and again and evaluate the object function again and again. But this actually, if you have a mathematical formulation of this entire simulation, this is actually not the only way to do it. There may be much better ways. This much better way is going backwards through the calculations, through the traditional way you are doing the calculation. The traditional way is, if you look at this formula, we are going from the right to the left. we are computing A times B, and then this we get a U, and then multiply U with C transpose. The adjoint way, which is also called the backwards, I mean that's why like in neural network they call it backward propagation. It goes backwards. We start from the left hand side of the formula. We compute how the objective function would be sensitive to the solution, which is C, right? And then we go backwards one more level to see, okay, now U depends on B. Now how does my objective function depend on B? So this C transpose A is the sensitivity of the objective function with respect to B. So from that, we go backward and we can get how the objective function depends on every single parameter. So let's generalize this example to a slightly more complex case. Okay? So for the slightly more complex case, we'll be analyzing only small perturbations because we no longer assume the objective function is linear, right? So here we assume that the objective function is linear. We'll also assume that the relationship between U and B is linear. In reality, a lot of functions we evaluate will be nonlinear. So the way out of this is to look at small perturbations, right? When we look at a small range of parameter S, when the range is small enough, we can assume that the effect of the small perturbation to U is going to be linear, even if the relationship is nonlinear. And every single step, if we linearize the relationship, we can use exactly the same formula to analyze how a small change in the parameter, how any small change in the parameter is going to induce a change in the objective function. In other words, we get the gradient. Right? The gradient is what we use to describe how a small change in the parameter affects the objective.